All right, so let's talk about waves. First off, there's two major kinds of waves. There's the longitudinal, and there is the transverse. And the big difference between the two is how the wave propagates. So let's take a slinky here. Couldn't find the right one, so we'll go with this one. I have a slinky here, and I hope you can see it well enough. If I let go of some coils at the top, magic is going to happen. What did you see? Dulce?
It looked like the coils were traveling up and down.
Now, how far did the coils actually travel? Yeah, just a little bit. Because, I mean, it's sort of limited. It's not like I let go of it completely. It does look like something shoots down to the bottom and to the top. That is a longitudinal wave. The particle, right here, this is considered the particle in this case, moves with the direction of the wave or against it. So it's parallel or anti-parallel to the movement of the wave. That's the longitudinal wave. Particles travel parallel or anti-parallel to the wave. So an example, we have a slinky. I'm going to call it the slinky pulse. And sound. Sound is a classic longitudinal wave. Because my vocal cord is vibrating back and forth, and so I'm pushing air molecules out. Those air molecules hit other air molecules, which hit other air molecules, which hit other air molecules. So it comes, the propagation of it, it moves because you got one thing smacking into another, pushing one thing. As opposed to transverse waves where it's more apt to be pulling. So in a transverse wave, the particles move perpendicular to the wave. And we will do a demonstration here. If people finish writing, because you're going to need to stand up in a moment. All right, we're going to do the stadium wave. So Emily, whichever group that you either, I guess, pick a side. But Ty's going to start us off. And what Ty's going to do is going to stand up and then sit down. And as soon as the next group sees him stand up, sit down, they're going to up and down, and then we're going to slowly work around. When you see the person in front of you, or next in line, stand up and down, you do it. And I've never actually filmed the students doing this. All right, I guess I should ask. You would rather I not?
It's fine.
Okay. Anyone rather I not? I guess you don't really want me to? Okay, then I won't. But at least whoever's watching this video gets to experience the earthquake. All right. Ty, whenever you're ready.
I just stand up.
Just stand up and then sit down. All right. That is a transverse wave. You as particles are moving up and down, but the wave moved around this way. Transverse. Now, we can also demonstrate a transverse wave, and we'll do this in a moment with this, and it's better when it's out farther than just between my two hands, but that's a transverse wave as well. Now in geology, this is an example of if there's an earthquake here, then you have this shock wave as part of the earth pushes against another part of the earth, pushes against another part of the earth. That earth pushing against earth, longitudinal wave, and those are the waves that are going to get to a seismograph first. Because longitudinal waves, because it is pushing against another atom or molecule, can travel through solids, liquids, and gases and plasmas. They get here first. They are they're called P waves, and that P stands for pressure or primary. Someone was talking about the earthquake in Turkey, and he called it primary wave, but I've also heard it pressure wave, and both work. They're the ones who get there first, thus primary, but it's caused by pressure, by one thing pushing against another, thus pressure wave also works. Transverse waves require pulling, so as one part of it gets moved up, it pulls the next part with it. Transverse waves do not go very well they don't go at all in gases. That means if they went well in gases, then you should be able to feel the breeze, which you, I'm assuming, do not. There we go. Eventually it'll get to you, right? Just because I move an air molecule doesn't mean it's pulling the next one with it. There's not a whole lot of interaction there. So the transverse waves really need solids to move through. Well, as far as the Earth is concerned, because we've got this molten core, and apparently something solid in the middle, they have to travel around the long way. So they will get here second, and these are called S waves, where S stands for secondary or shear. And this has given us our best clues about what's in the center of the Earth is based upon this. I don't know if you've seen that they talked about that the inner core. There's so much pressure here in the middle that it's basically solidified. You heard recently about it switching directions? Just one of you? Two. As with anything dealing with speed or direction, it depends upon the observer. It is now traveling slower than the surface of the Earth. So from the point of view of on the Earth, it looks like it switched directions, but it's just traveling in the same direction it was before, just slower than the surface, whereas before it's going faster than the surface. At some point, though, the plasma in the middle will switch directions. And at that point, the poles will switch. But that's for the plasma, the caramel nougat, that is right there. All right, so those are the two type waves. Now, in terms of drawing them, they're going to look very similar, just have slightly different meanings. For transverse wave, that could be a physical representation of the side, a side view. Battle ropes, people familiar with what battle ropes are? Have you seen those long ropes attached to a wall sometimes in gyms where you do this? Those are, I've been told, called battle ropes. It's just a bunch of transverse, you're sending transverse waves down, it hits the end, and then some of it bounces back. So if you're doing a side view, transverse wave. So this would be a physical representation of what's going on. Longitudinal waves, well, you think about sound. Sound, I've got air molecules, so I've got a bunch of air molecules. And then I've got other air molecules over here. This is not easy to draw every time I want to talk about sound. Because they're supposed to be dots, if not this line. So representing a longitudinal wave like this might be a better physical representation of it, but it's a nuisance to do. And so I'm still going to draw longitudinal waves with a curve like this, except for the longitudinal waves, this would represent a high concentration, or in the case of sound, pressure, and this would represent low. And I tried to draw it sort of like that. At the peak here, I drew a lot more dots, and at the trough, I drew a lot fewer dots. So this would represent this. Now there's one other way to draw these, where you're just sort of an overhead. Think of ripples in a pond. I've got a very still pond, you throw a rock into it, and you get this ripple going out. I could also draw the same thing by just a line here, and those would represent the high concentration or a high pressure. So if I threw several rocks into a pond and managed to hit the exact same spot, that would represent each of these would be where the wave peaks, higher concentration of water or higher depth of water. In the case of sound, this would represent the high pressures, and then the low pressure spot is in between. All right, so basically you can use similar representation for each of the waves, even though they're slightly different. Oh, and by the way, and this is in the video too, but I don't want that one. This area right here where you got a lot higher concentration, this is known as compression. In the place where there's not many, rarefaction. Oops. Yeah, that's the way I've heard it pronounced, rarefaction. I know there was a test question at one point about, it was multiple choice, and the gist of it is sound is composed of compression and rarefaction. All right, questions before we do a little vocab, a little extra vocab?
You said it was sound that was comprised of compression and rarefaction?
Yeah, rarefaction. All right, there's certain vocabulary words also associated with waves, and so we'll start out with the word frequency. Now the word frequency in physics is very similar to the word in everyday English. It's just how often something occurs. Often. Since we're talking about waves, we can also, I'll use the term waves or I'll use the term cycles. A cycle is just a wave. It's something repetitive that happens again and again. So the frequency would be the number of cycles per time. So if something happens 5 times a second, the frequency would be 5 times a second. If something happens 5 times a minute, then it's 5 times, then the frequency is 5 cycles per minute, or 1/12 cycles per second. Yeah, that's right. Now, in terms of units, because everybody loves units, the units of frequency, the SI units of frequency, are, well, it's cycles per second. But there's a one word for this. Anyone happen to know what that one word is?
Yes.
What'd you say?
Hertz.
Yes, hertz. Hertz is capital H, lowercase z. The abbreviation. It is in the video, but the symbol that I use for frequency, as noted right there, is the F, the same F that I use for friction. Fortunately, we aren't having to deal with friction and frequency in the same problems in this course. Unfortunately, there's another symbol that is often used for frequency. Anyone happen to remember what it is for those who have seen the video? I'll take that as a no. It is the letter nu. I do not particularly care for this because it looks a whole lot like a V. Matter of fact, depending upon the font that is being used in the textbook or the website that you're looking at, nu might look like that and V looks like this. And then other websites, the nu looks like that and the V looks like this. It can get very confusing. There's a formula that we will come up with where a formula that's going to look something like that. And whenever I'm looking at a textbook and I have to figure out, all right, is that a V or a nu? I look for this equation because I know it's going to be V is equal to, if they're using nu times lambda. We'll explain what this equation means in a moment. But this is what I have to look for in order to know which one's the V and which one's the nu. I only bring this up in case you run across it elsewhere and you go, oh, yeah, that's right, he said something about this. But that potentially is the last time I ever write the nu up here. All right, next vocab word, period. Talked about period already. The symbol I use, capital T, and it's the time to complete a cycle. So if I have any repetitive motion, the period is the time to complete a cycle, to complete one cycle of repetitive motion. Or it's time divided by number of cycles. If it takes me 5 seconds to, let's do an even number, say 24 seconds to do 6 cycles, well, the period is 4 seconds per cycle. So this is basically time per cycle. Which is just the reciprocal of frequency. So we have this relationship here that frequency is 1 over the period, or the period is 1 over the frequency. And what would be the units of period? Absolutely. wavelength. The symbol I use for wavelength is a lambda. There's a B in lambda. Someone once called it a drunk T, because it fell over. But it's the Greek letter lambda. And it's just how far a wave travels in a period. So what would be the SI unit for wavelength?
Meters per second?
That would be a speed,
Meters.
meters per second.
Meters?
Absolutely, meters. It's how far, it's a distance. That's for the most part, the bulk of vocab. There obviously more will come off, but we got the basics down here. Questions up to here? Elsa?
Is it possible that you'll ever confuse the F for frequency with the F for friction?
Not in this course. No, I